Okay. Good morning, everybody. Welcome to a new webinar for the MPI project. Today is my pleasure to introduce you David.
I can't hear Jesus.
Yeah, sorry. I think that Jesus is not. Sorry.
Yeah, I'm here again.
Okay.
I don't know why I was on mute. It's my pleasure to introduce you David Esposito Sin and Alberto Cascajo from UC3N. They are going to talk about the implementation of FlexMPI and the integration of this FlexMPI technology with the intelligent controller that we are going to use in the project. So in order to remember that we are keeping this session recorded and to have the video in the web, so it's better to probably leave all the questions to the end when we close the recording, okay? So thank you, David, and thank you, Alberto, for the presentation, and now you can proceed. Thank you.
Okay. Thank you for the introduction. Hello, everyone. So, as Jesus said, the idea for today is to introduce FlexMPI, the work that we have done, and how it's currently integrated in the context of our MPI project. I think that this presentation could be useful in general for all the admires members, but specifically for the application people. The idea is that recently we had a survey from you for understanding better how the applications work. And with this presentation, the idea is they can just get an idea about how the runtime FlexMPI is implemented, what are the potentials about it. Maybe later in further meetings, we can discuss if it is suitable or not to be integrated with the applications in the context of MPI project. So regarding questions, all the slides have a number. So please, you can just keep the question and the slide number, and then we can address all the questions at the end of my talk. This is the outline. Okay. So first of all, I'm going to introduce a few concepts about malleability. Then the idea is to do something incremental. So then we'll provide an overview, the capabilities of FlexMPI, then practical examples about the work that we have done that I think is interesting just to see, maybe you can get ideas about possible use of FlexMPI or malleability in general for your applications. And then we will go more into the details about code structure, function calls, and how it works internally. Okay, I think that is an important part of my talk. Finally, I will mention how it is integrated with the intelligent controller, with the new communication protocol, and finally I will show you a demo of practical use case in our cluster. Okay, so let's go first to the introduction. The introduction is going to be very brief, just to define the 5 different categories of works according if they are elastic or not, malleable or not. Okay, probably you already know this definition. A rigid job is something that cannot change the size. Okay, here I'm focusing mostly in CPU malleability. So I'm talking about number of processes or number of threads. Okay, so the size of a job is proportional to the size of the box, let's say. The starts execution here, okay, this is the time. So rigid means not variable, fixed size during all the job execution, okay? Moldable just provides certain capabilities for changing the size. The thing is that these are applied at the beginning, at the very beginning of the application, okay? So it's a request to the RMS, Resource Management System. Could be SLAM, for instance, in a real platform or any other equivalent runtime system of the platform. So according to the existing resources, the RMS sets a certain size for the application, sets a certain number of processes. The application takes this size and then does the whole execution with this fixed size. So jobs cannot change during the program. Okay, of course, we are going from less restrictive to from more restrictive to less restrictive. So the next category is evolving. In evolving, an application can request this function. Okay, it is requested to the RMS according to the existing resources. Can be done here. We can see that originally the size is reduced, and then according to decisions taken by the application, probably a certain phase is better to use more resources because it's more compute intensive, for instance, and it's scalable. So ask for resources, and if they are applied, if they are agreed, then the application performs malleability. This is actually a malleable operation, changing the size. Okay, this can be done at any point of the execution and during as many phases as is required. Okay, but look at here. The thing here is this. This is one way communication. Okay, from the application to the RMS. Okay. The fourth category is malleable. Okay, malleable, the actions, the decisions are taken by the RMS. So the system, runtime, the size, which is the best configuration for a certain time application, and this configuration is applied to the job, changing the size. So the decision is made, taken in this other side. Okay, and just the last one. Okay, the last one is adaptive. Adaptive includes both of them, so it can be taken from the RMS or from the job. Okay, so it can be done at any point of the execution. And just think about that. The difference here is where is the logic, because we need decision logic about where is the best, what is the best configuration of the application. So here the decision logic is here in the RMS, or in this other case, the decision logic is in the job, in the application itself. So here I have the freedom of putting the logic in any of these places. Okay, I can't. I would like to have feedback from you during the presentation, but I agree that it's better just to continue. Okay, so this is, I think, all we need for start talking about FlexMPI. Okay, so I'm going to start introducing it. It's a runtime, okay, written in C, and we use MPI internally. Okay, it is originally focused on address to simple program multiple data parallel application. You know, this paradigm basically in here, all the processes perform the same actions. The difference is that they work on different data sets of the whole program. Okay, but the work related to each process is the same code. Okay, and in FlexMPI we have three basic components. First is a library that is executed with the applications. The idea is that the library contains functionalities for providing malleability and other capabilities that we'll describe later. Also, we have an external controller that coordinates the execution. This is equivalent to RMS system like SLAM, also kind of equivalent to the intelligent controller, as I will describe later. So have logic in FlexMPI in the library, and also logic, decision logic, in the external controller. And recently we have included an interface that is in a way of another library that provides different communication protocol using RPCs with the Admire components. It was developed a few months ago, and with this we are able to connect FlexMPI with, for instance, the intelligent controller in Admire. Okay? So here's the information, the link for the source code that is available. Okay? I think that's worth mentioning that this is quite old project. We started in 2012. The first version was released 3 years later. We have done, these are few selected papers related to this. The original ones were related to, as we'll see, data redistribution that is also managed by FlexMPI. And then with the work in different directions, including optimal or let's say performance-oriented malleable techniques, for instance, energy aware, malleable techniques, I/O scheduling, and multi-criteria scheduling of applications. Okay? I will describe some practical examples related to these papers in later. Okay, just to give an idea of the potential of FlexMPI. So going more into the details. Okay, if we look at the previous definitions, FlexMPI provides both malleable and adaptive capabilities. So it's malleable because we can connect it with a resource management system, so receives commands. In our case, in the context of ARMIDE, it will be the intelligent controller, receiving information and commands from it, but also has some logic for taking decisions inside the application according to the application state. This is more adaptive. Okay? We have already implemented different policies, for instance, trying to find the maximum application performance, taking into account the application speed up and the existing resources in the platform, or for instance, trying to find a trade-off between execution time and efficiency, operational cost, or energy consumption. So we have developed previous work in these directions. Okay. Also includes load balance. I think that one interesting feature of FlexMPI is that all the application data is automatically and transparently managed by FlexMPI. So if a new process is created, data is automatically distributed for this new process. Or if there is any problem of load balance, data can be redistributed just for that. Just think about that, as I said before, we are considering simple program multiple data applications. So if we, the computation follows the data. So we distribute the data. What we are actually distributing is the application workload. Okay, this is why we perform load balance. And also we have developed a runtime monitoring. FlexMPI provides that. In this project, there are other tools more advanced, but we have this capability, and I will show the information about that during the demo. Okay. So this is for FlexMPI. For the controller, the external component basically is scheduling, application scheduling, and I/O scheduling. Also, for I/O, we use Claris runtime. That is a different runtime that was developed in our group. Okay. So the purpose of this part is just to provide an outline about the structure of FlexMPI. Then we will go into the details about how it works. Okay, so the structure is something like that. We have the application here, okay, and we consider three different types of calls. Okay, so we have basic MPI calls, for instance, the one that are managing communicators, for instance, that are unchanged. They are just directly send, or they directly call the MPI library. Okay? Other MPI calls, like MPI init or end, are wrapped via PMPI interface. Wrapped means that we don't change the syntax, we don't need to modify the code, okay? But during this call, it performs the original purpose of the function. For instance, MPI init just set up all the MPI environment, but it is also used to setting up, configuring the FlexMPI environment. Okay, this is done transparently, and with this we can just initialize and also monitor the applications. For instance, communication and I/O calls are also wrapped. Okay, so we can monitor these calls by means of FlexMPI without introducing any change in the application. The changes in here is in the interface of the library, MPI library. By the way, we use MPI library. And this interface just is very simple. We don't need to modify the library, just to put an intermediate layer here. So it's quite modular, not intrusive, and transparent. Okay. Unfortunately, FlexMPI is not perfect. We need to introduce additional calls. One of them is like here, XMPI. So are specific calls, just for instance, for defining the malleable regions or for defining, as we'll see, registering data structures that the FlexMPI is managing, for instance, is redistributing when it's needed. Okay? So there are additional calls. Later, I will show you a code, okay, with the example of these calls. Okay, so this is the idea. This is the library. Okay, and we have two different levels in the library, two different uses. The first one is malleable configuration. The malleable configuration, the logic is quite simple because it basically receives commands from the resource management system, RMS, saying, okay, let's create a certain number of processes. This FlexMPI is passive. It doesn't take any action. Okay, so for doing that, we need just very few modules, just load balancing, data redistribution, and dynamic process management that are functionalities for creating and destroying processes. Okay, the connections comes here. This is an external component. As I said before, in the context of Admire, this will be SLAM with an extension that we are working in currently. And we use the PAPI library just for collecting monitoring metrics. This is optional, okay, but I put it here because it's interesting just for getting information about the execution status, okay? So this is the first configuration of FlexMPI. And the second one is the adaptive one. You know that the adaptive, the application is able to take decisions about if it is necessary or not to reconfigure. Reconfigure means create or destroy application processes. So in this case, we have more functionalities just for monitoring actively. We have developed models for predicting the application performance, decisions, policies for reconfiguring according to certain performance criteria, according to energy also. And also taking into account different applications, different processes. So we also have implemented a scheduler, can be in the library or can be external in the resource management system. Okay, so in this way, we are free just to have a passive FlexMPI use or an active one that is able to take decisions. Okay, it's up to the programmer which one is better to use. Okay. In the context of Admire, this is the approach that we are initially following, but we also want to leave the door open to use the second one, maybe at the end of the project, okay? Just to provide an additional way of malleability. Okay? So that was the library. Now the controller. The controller is external, okay? You can think about like here, the intelligent controller. Okay, that was designed before the project, and it is originally run in the same cluster, not necessarily the same compute node. The communication is by sockets, okay? And the controller, there is one controller per platform. So all the running applications that are using FlexMPI are connected to the controller. It's very important that the connection point is just one per application. So in this example, we have one application running in with two processes in two compute nodes. It will have only one connection line with the controller. It doesn't matter if there are two processes or 2,000. Okay, it's one connection line with the controller, so the contention can be reduced or avoided because the maximum number of connections will be the number of running applications in the system. Okay? So the controller deploys applications, it's a kind of scheduler. It's also able to communicate with applications and receive data from them, and also take the decision about terminating our application if necessary. Okay? Here is an example. This is the list of commands that we have implemented. The commands are related to functionalities implemented in FlexMPI. Okay, I will briefly describe them later. Let me show one example. For instance, create a new process. Okay, so the application that before was running with 3 processes, now it creates a new one. We can specify the exact compute node where the process is created. So we have full control about the malleable operation. The same way we can destroy the process, any process of the application. Okay. The communication is done, as I will introduce later, by a listener. Okay, so the rank 0 process, the root process, has a thread. This thread belongs to FlexMPI library that creates the connection channel with the controller. Okay? So this is information that is sent to the FlexMPI, and this is information that is received from it. Okay, so we can just using the command for activate the monitoring, can be activated or deactivated. Just check, look for the time, and we can just receive monitoring. A new thread is created, and monitoring data is received. Okay, in an extra thread created by the controller, so we can just monitorize the application. Interesting thing here is that the information is collected by the application itself, and it can include internal variables of the application. For instance, the iteration number. So we know at which point of the execution the application is being executed. Okay, this is an advantage of using internal application monitoring. Just regarding the rest of the commands, okay, just very briefly, we can just define policies that are used by FlexMPI in case of being adaptive. Okay, load balancing, information about the last control point, the variables and performance related to it, monitoring, terminated application, just creating malleability immediately, sending the commands just for create an immediate, as I showed before, malleability reconfiguration action. We can use PAPI library, so we can define which are the hardware performance counters that are monitored in the applications. Maybe we can just unchange them dynamically. So we are running the application, we can just collect information from cache misses or TBL misses or flops or whatever is supported by PAPI. Okay. Other thing is core binding. It is if the operating system supports that, we can just map processes to cores using FlexMPI. 2 more about I/O. Okay, we can just do I/O operations. And the last one that I think is very interesting, we just discussed it in a previous meeting, delayed malleability. You can just specify a time triggered event. For instance, I know that the application iteration now is 1000. So at iteration 2000, perform this action. So we can just leave and program a pre-configured malleability action, creating, for instance, 3 processes at a certain time in advance. Okay, it's another option supported. Okay, so these are the functionalities, and then what we have done, I'm just going to briefly provide an outline of the work that we have done with it, because we just increased the components and complexity of the runtime. Okay, so we have one work I will show you later briefly, very few results, where I have several applications with FlexMPI. We monitor, in this case, we monitor the I/O, timestamp, and intensities. And what we have are, we have models, okay? So we have models that we are able just to model the I/O and predict the incoming I/O phases. This is done dynamically at runtime. So we are able, you know that I/O presents variability. So maybe it's not possible to predict what is going to happen in the following 20 I/O phases, but we can get an quite approximate prediction for the next phase or the following 2 I/O phases. By the way, I'm assuming that in this context, an application has different phases, maybe CPU first, then maybe I/O, okay? And they are periodically executed. We alternate different phases. So with this, basically, we work with models and we predict contention. And in case of having contention, with malleability, we are able to avoid it. I will show you an example later. Okay, so this here we involve monitoring models, combining data from models, and taking malleable decisions about the application. Of course, one line about I/O. Another one line very recent related to Alberto that is in this meeting, related to, he did it in his PhD, is multi-criteria scheduling. So we developed a scheduler, actually it was a scheduler and a resource management system connected both with FlexMPI and a monitoring tool. Okay, so we perform monitoring at node level, like in this project, but with a tool that we used, and at application level using FlexMPI. Combining both information plus the information of the system, users, here Claris, that is another runtime for I/O scheduling. We develop different scheduling techniques. Okay, again, I will show you examples just very briefly in the following slides. Okay, so basically what I want to summarize is that FlexMPI can be integrated and extended with other components working with in the directions of this project, because I think that most of these goals are also part of the ADMIRE's project. Okay. Just a couple of slides about applications. Okay, currently there are 3 kernels that are integrated with FlexMPI. First one is Jacobi method, that is a dense matrix method. Conjugate gradient kernel, that is also a numerical method that uses sparse matrices. And we have developed, I think this is interesting, a synthetic kernel that basically alternates different phases, and the length, I mean intensity of each phase is parameterized. So we are able to define multiple patterns, for instance, applications that are very I/O intensive with a certain I/O duration and a space between the phases, or just pure CPU phases. I think that is, at least for us, was very useful for testing purposes, and this application is available and installed in our cluster and now fully integrated with the intelligent controller in the prototype that we are developing. Okay. Yeah, of course, if you need more information about any of these parts, we can discuss it later or by email, and we will be happy to answer your questions. Okay. We have also one application that was developed in our group that is an influenza and COVID-19 simulator. It's a parallel tool, use a huge amount of data, perform simulation at different scales, national level, European level, communication intensive. And one thing that is, one property that is quite interesting, here for instance, we look at the incidence map of, in this case, was influenza. And in this curve, you have the one prediction, red is real data, blue is simulated data for COVID, was the first wave in Spain. And the thing here that is very interesting is that the computational resources depend on the number of infections. This is the number of infections. So the higher it is, the more resources it needs. Okay. So the CPU and communication phase, the intensities change during the time. In this point, the CPU phases are more intensive because the application is more compute intensive, more infections are being calculated and data is being moved. But in this part of the simulation, there is very little CPU, but there are a lot of communications because the iteration runs faster, they need synchronization, they need to update the system, transportation also, that involves MPI communication. So in this part of the application is communication intensive, more communication intensive. And the funny thing is that it depends on the shape of the curve. So you have a different distribution, will have a different behavior. So I think it's interesting, not only for now we are doing a lot of research with COVID-19, but also from computational point of view. As an interesting problem that is now malleable with FlexMPI. Okay, it's integrated with it. Okay, so with this part, I finished the outline of the overview of FlexMPI. I'd like to just briefly show you a few examples about what we have done with it. Okay, just maybe can be potential ideas for your research, okay, or for developing algorithms. That is another part of the work. Okay, I hope that they are useful for you. So one of them is load balancing. It's not related to malleable, but just basically given that we are able to automatically redistribute the data and the workload, we basically, here the blue is an external application sharing the same compute node. Okay, so we are able to, and this is, sorry, this is the processor time, okay, the CPU time that is related to the application CPU use, CPU intensity. So if there is another application that takes resources in this node, so the original one, the red one, decreases the performance because it is sharing the resources with the other. Okay, so we have, using monitoring inside FlexMPI, we are able to detect it and redistribute the data, okay, in order to avoid this thing, of course, until certain limits. Okay, it is not possible to do it completely. Of course, there is another solution that we are also doing, that's that using malleability just to move the application to a different node, completely. Okay, so we are able to partially avoid interference, CPU interference, I mean performance degradation, or completely. Okay, so this is one line. Second one involves malleability. We have done work using, in this case, a cluster with different, the point here is that we have different compute nodes. So we have different hardware, okay? So okay, certain application can be run in nodes that are maybe faster than others, but they might have a smaller operational cost, that is the cost per hour that is related to the node, okay? So based on that, we have developed policies just trying to maximize efficiency, I mean, minimize the execution time, just for instance, choosing the nodes that are faster, but taking into account application scalability. That's very important, okay? Taking into account if it is worth or not using the nodes. Here we have the time, the nodes that are being used. In this example, we increase the number of nodes using malleable, so the application expands, okay, for doing that. But maybe the objective is different. Maybe the objective is the cost. Cost is difficult because maybe there are nodes that are cheaper, but the execution takes longer. So there is a trade-off between execution time, because of course you pay at the end is the duration, the execution time multiplied by the cost. Okay, so there is an optimization problem that is implemented, and based on that, again, we take decisions about, in this case, these nodes are more cost efficient than the others. You can see these peaks. So these peaks is that for us in our experience, all the algorithms are runtime algorithms. So all the decisions are made at runtime based on the existing data. This allows us to introduce corrections. Corrections saying, okay, we are just behind the schedule, just put a little more processes for a certain time in order to meet the required final execution time. Okay, so this is done, and of course we take into account the overheads of the data redistribution, that is, and process creation, that is a handicap here. So the techniques collect all the information and make decisions in order to achieve the desired goal. Okay, this is one line. Another was energy. Energy was more difficult because here we can see two different compute nodes, again, different technologies, different families of the same processor. According to the number of processes, two different applications, the curve is different. Okay, so here the power consumption is smaller, but of course maybe the execution time takes longer. That's the problem. Okay, because this compute node works at a lower frequency than this other. And another thing interesting is that this curve is not linear. So the power increases at a certain limit. So in this area, we can just change the number of processes without a big penalty in power. Okay. Based on that, we have developed policies just, for instance, trying to maximize the performance per watt. For instance, MIPS per watt or flops per watt. That is one goal. Or try to minimize the energy. In this case, for instance, we can see that these are the compute nodes, a different set is selected. This is more energy efficient. This is more performance watt efficient. Okay, and again, the algorithm reconfigures according to the goal. There is a constraint of execution time, so it is able to adapt during the application execution. Okay, introducing changes in the number of resources. So this was another line. Okay, just finishing, just two more, just to finish. I/O, that is another research that we have made. So two different applications. If the I/O is big and for both of them it occurs at the same time, there is risk of I/O congestion. So it is called here as interference, which means that the execution time may increase because there are two different applications writing in the same device gigabytes and gigabytes of information. So this can be avoided in different ways. One of them is to delay one of them, but if you delay it, you just block the application. Just for instance, if we are using 1,000 processes, we are blocking for several seconds or minutes. The system is not very efficient. So the idea is to use malleability to just advance one of the phases because we create processes, okay, in order to avoid the congestion. The advantage of this is that we are not losing time. We are actually saving time. We have overhead, but the overhead can be put in here. So if the application is scalable, if, for instance, we need to create 20 processes and there is a certain overhead, maybe with 25, we just avoid this overhead of data redistribution. So in this way, we can just avoid the interference, the contention, without wasting resources in the system. It's important to mention that, again, runtime. We need to run the application, see when is the incoming, work with models, model the application, based on them, take decisions. Okay, make decisions about what is the action that has to be taken. Okay? And just the last one, multi-criteria. Here we used FlexMPI in a different way. What we did was to just use malleability to move one application, migrate from one node, removing the nodes from the processes in this node to another, creating new processes in a different node. So the idea is that we have here two different applications sharing the resources, okay, without oversubscription. If we monitor both of them, so if there is not a conflict, they don't interfere with each other, we can leave them because we are using better the system. We are just using less compute nodes. We are sharing some of them. But if there are problems of interference, for instance, one application has a poor data locality, produces a lot of cache misses that also degrades the cache performance for the other one. In this case, we are able to detect it and to migrate it to another goal. So this is a multi-criteria scheduling. These curves are from Epigraph, the COVID simulator. So we have here two waves of COVID in Spain. I think that, yes, the blue one is Epigraph, and we can see that running the same node, another application can, that is a benchmark, the performance, okay, iteration time is affected by Epigraph. So in this case, we detect, and when in the valleys here and in here, if they are wide enough, we just decide to move it to a different compute nodes and avoid this degradation here. Okay? Otherwise, they share and we have less compute nodes in use in the system. Okay. Okay, so I hope that was clear and useful. These ideas. Just a couple more things to mention before the demo. First one are the internals. Okay, what do we need to do to introduce the code? So there are two examples. Okay, the first one is the simple one. Okay, so this is the original code. This is just a very basic one. We can see in red MPI calls. Basically, you see, you know MPI. Okay, we initialize the library, define the run size, then we have a loop. Okay, a certain number. This can be, for instance, a kernel of Jacobi or conjugate gradient. Have different iterations. It's an iterative system. We have data dependencies between the iterations. And here we have another loop just for instance, accessing to the arrays, for instance, performing matrix vector product or solving set of linear equations. Okay, usually working with matrices. Okay, in this example, we are assuming that there are not matrices, just to simplify the analysis. Okay, so pure CPU time. Here, no data structures, maybe one communication, MPI communication related to anything not relevant at this point. Okay, and that's all. And then program finalize. Okay, how do we need to transform it? Okay, sorry. First, you can see in purple some of the calls original are wrapped, which means that we don't need to introduce changes, but the MPI library uses them to initialize FlexMPI library, terminate FlexMPI, and for instance here monitor the all reduced communication. Okay, then there are specific FlexMPI functions. Okay, these are called support functions. For instance, in here we specify the size, the iterations assigned to a certain processor. Okay, if it is a root, just root is executed at the beginning, you get the same as the original code. Okay, also here we can know if the process is native, which means that belongs to the original execution of the program. Okay, or it's a new spawned process, a new created process. So in this case, we need to get the iteration number, the current one related to this control point. So now we see that IT, okay, now it's not 0 because a new process will get the value, for instance, 1000, and will start running the program in 1000. You can think, what about the state? What about the state? Okay, the state, we assume that is related to data structures. This example does not have data structures. The next one we will have. So just focus on how we identify the new one, iteration, and then two control points that are important. Okay, this is used to define the beginning of the malleable region, and this is used to define the end of the malleable region. Also, we monitor data in between. This is why it is called monitor. Okay, so these are control points for defining the region. Okay, and based on that, for a new created process, we get the iteration, we start working on it, independent parallel computations. I'll look at here, sorry. Each process will have, we use offset length structure. So the original iterations that, sorry, they should be split in here also. There's parallel. They are also split by these two data structures provided by get W size and also monitor end. In case of changes, these are get here. As I said before, simple data, simple program multiple data, okay, that involves working with different chunks of data. The location of each chunk is given for each process by these variables. Of course, they are different for each process. Okay. Okay. I hope that it's clear. At this point, it should be nice to have feedback from you, questions, because probably you will have. Okay, we can discuss then later. Let's see what happens with the state. Let's see what happens if we have data structures. Okay, So now have here an array that is initialized in the original code, no FlexMPI, and here we use the array, whatever, we can read, write on it, whatever operation. What changes do we need to introduce? We need to register the pointer of the structure and see how it is distributed. It can be disjoint, distributed in blocks, can be shared, which means replicated, or it can be even a sparse data structure that in this case, you know, have different arrays. I will show you a figure later that is distributed but not in blocks. Okay, so if it is the original one, looking at this state, it's native, then we initialize the data structure as the original code. But if it is a new created process, now we get a pointer to it using an extra function. So the idea is that when a new process is created, the program is stopped, we redistribute the data, and for each process, we provide new limits and a new data partition. If it is a new one, it will have a new pointer in here, okay, that will point to a portion of the data structure, A, in this case, that is related to this newly created process. Okay, so we need to put some lines, yes, okay, but if we look at the code, not many, just one per data structure that is being used in the program. Okay, here it's the same. We work with the chunk of A that is assigned, and the only thing that we need to do is, okay, if it is an already running program, maybe if the data was redistributed, we need to get a new pointer. Okay, this pointer will only change if the data was redistributed, for instance, for load balance or when a process was created or destroyed. So in this case, we get it, okay, and we continue the execution with the new memory layout. Okay, this is the other line. I forgot to mention, if a process is removed, we can get the status by means of this function, and if it is removed, it exits and terminates, okay, the loop. Okay, so that's all. There are few functions, okay, but basically just to register access to the data. On the other hand, we are distributing the data in a transparent way, so that's good. And also control points for defining the malleable section. Okay, okay, so with this, just some examples. Okay, these control points define a sample interval. They are internally only, we call the function every time, but the actions are only taken under certain iterations, for instance, every 1,000 iterations, just to reduce the overhead. This is called sample interval. Here is 200. Okay, so we run the application without intervention of FlexMPI, and then at 100, then we see what happens if there are changes. For instance, it's necessary just to do a reconfiguration, decision made by FlexMPI, by the external controller, or there is something waiting that has to be applied at this time. Okay, so we can define the signs of this interval, and this allows to reduce the overhead of FlexMPI. So we can do it, for instance, every few minutes of the program execution. The weight of this function is not very big. Okay, this is the main loop of the program. So here we basically monitor data, evaluate decisions every certain iterations. The cost is the same. And in here, if there are no data redistribution, we get the same address as before. So the overhead is not very big. We have studies in the papers about the overhead. The major source of overhead is when we have to redistribute a huge amount of data. That could be a problem. And for reducing that, we are working in a direction for using thread malleability also. With threads, we will be able to create malleability in node, malleability without data distribution. This is ongoing work. Okay, regarding the communicators, there is issue that the application have to use a different communicator, but basically it's just change the name. Okay, so originally the FlexMPI communicator that here is called XMPI, now is called eMPI, is just put in the, replacing the existing one, the default one. They are equivalent, but now, if for instance we create two new processes, you see here, these processes are merged into the communicator. So now, sorry, the XMPI communicator will have if all the processes, 5 processes. So we perform a collective MPI operation, all of them will be involved. Okay, so FlexMPI works well with collective operations. You may think, what about point-to-point operations? Then can be more difficult. It's something that could be possible or not, but the odds are not good for point-to-point communications. Okay, the same for removing. Okay, you have the communicator, FlexMPI, and if we remove one of them, it is just spelled from it. We keep the remaining ones, and this is destroyed, okay, including the process. So in the end, from the application side, the only thing that we need to do is that in the kernel, all the MPI calls that are related to a communicator replace the communicator name by instead of MPI, AMPI or XMPI. Okay, no more than that. Data redistribution, as I said, done automatically. So if we create one, we create new portions of the data. Here is unbalanced, but we can rebalance the data. Of course, maybe we need to move a lot of data. Have to be careful with that. Using control points, we guarantee also the consistency in the problem. This is a major thing, just to keep the application state. We have all the data structures registered. So using that, we can keep the state and don't change it if there are malleability operations. Okay, so just redistribute the data, but we keep all the data in the existing processes. This can be done for dense matrices or sparse ones. So if you are working with the sparse data structures, we have support for them. And of course, we can apply load balance. That is very interesting. Okay, automatic load balance for according to the sparse matrix pattern that we have. Okay. Okay, so that was the end of this part. Now the next one is the integration with intelligent controller. This was a work that was developed in the last months, mostly by Clement from Intria and Alberto from UC3M. Okay, so basically this is Admire's project, intelligent controller. These are the application, and here is FlexMPI. So what we have done is we have developed an extension that is Admire Application Manager that is able to communicate with the intelligent controller. Okay, this is, I'm going just to discuss the internals of that because they will be useful for the rest of the team members that have to integrate, for instance, scheduler, malleability manager, ad hoc storage, communicate them with the intelligent controller. Okay. So as we discussed last year, we decided to use an RPC library that is broadly used in HPC environments. So that was implemented in intelligent controller for connected with this component. And the idea is that want to do something that is simple, consistent, and transparent to the users. Okay, protocol that does not once this is implemented, for instance, the application people do not have to be even aware that this RPC is being used. Okay, it's completely transparent to the application. Okay. The code is available in this repository, and there is a library called libICC that was developed, including this library includes this RPC environment. Okay, just to summarize the idea. Okay, so now we are talking in Admire. So now we have the intelligent controller. Okay, As you know, intelligent controller has different components. It's a multi-threaded system. One of them is the malleability manager that is in connection with the application. Okay, there is that I will mention after. There are two different kind of connections, bidirectional and unidirectional. I will describe them later. And we have threads. We have threads here and in here related to the RPC library. This is the new component that was developed. Okay, again, only one component per application. It doesn't matter how many processes we have. There will be only one RPC library, okay, related to it. So all the internal communication is carried out by FlexMPI. Okay, so FlexMPI is internal. For instance, monitoring or receiving. For instance, when we receive a malleability command, it's sent here, and FlexMPI sends the command to all the processes just to take actions. Okay? So there are basically two protocols. Okay, one is if you remember the idea of the architecture. Have two different ways. One is calling directly the certain, for instance, here we call something that is in here, but we also need to do a callback. A callback is registering a method here, so the intelligent controller is also able to call function from the malleability manager. Okay, so we have these two different arrows. Here, the active part is the malleability manager calling the function here. And in here is just the active part is the intelligent controller. So what we have done is two protocols. The first one is by means of a callback function. So we register this function, and then the other component is able to call this function and send information. The information format is generic. Okay. And the other one is just called unidirectional RPC. We just call the original function that is published, it's available, and we send data. Okay, so this is just one way, and here we are able to register and receive calls from the other channel. Okay, I think that is better seen in this time diagram. So this is the one-way thing. So we have here the register, the general RPCs are registered, are available by means of the library to the application. This is the application FlexMPI. Actually, it's the library that was developed. Okay, so we are able to call, receive the information, store, for instance, monitoring information, and the application just send monitoring information, or for instance, control points, starting and ending of the malleable region. So we call it as many times as we want. So the intelligent controller is aware about the state of the running application. Okay. The other thing is callback. So in callback, we want that the intelligent controller send information to the application. For instance, create certain number of processes. So the idea is that I have a service. The application register the callback into the service. Okay. So the intelligent controller keeps this function that can be called. We use Redis as a database, and then when the application is being executed and if actions are taken, then we can use the callback to send information. So we can access to the function, call it, send the command, and the application will receive the command. Okay, and take the actions, for instance, reconfiguration, expanding. Okay, so this way is a callback way, and using that, just it's important, are generic calls. They can be used, this for all the components in the admired architecture, fully generic, within the name of functions or information that is exchanged. Here I have an example. I have a discussion with Alberto that was involved about the intelligent controller. Given that the intelligent controller is internal and is quite complex, I think that is not worth mentioning during this talk because we only need to interact with it. So this is the part that is in the application. This is the part that we only need to write. And here we see that it's quite simple. There are very, very few lines. For instance, one-way call is basically we use the init just to send the information. Okay, have the payload here, the amount of data, and we have a handler, of course. So the information is sent. Okay, and with this we know about the outcome, the execution. And in here is for the callback. So we basically just register the callback.
Sorry, David.
Yeah.
The first one is the one-way RPC.
Sorry, I saw it
Yeah.
wrong. Thank you,
Yeah.
thank you, Alberto. Yeah, I didn't realize because we
don't
changed
worry.
it before. Yeah. So this is for the callback, sorry, and this is for the one-way communication. Okay. So I think yes, it's here when we can just call. And the nice thing here is that once it's registered, we can call it as many times as we want. Okay, we don't just only need to register, connect the components once, and then reuse the call. So the overhead is just very, very small related to this RPC call. Okay. Thank you, Alberto. Okay, so this is an example, but what I'm going to use is I'm going to use the example, a short demo, just to show how it was. So just to finalize in the context of MPI, the intelligent controller will be connected one hand with the malleability manager using RPCs, also with the RAM, okay, that will be responsible of also allocating resources or terminating applications. This is another direction that we are working in. And of course, with the rest of the application of the runtime, okay, using this RPC library. So here, we just left these slides as an example in text, just in case you want to download the slides and look at very briefly without looking at the demo. So here, the last slides, you have the example. And for me, what I'm going to do is I'm going to use a video, okay? Unfortunately, was a major hardware upgrade in our cluster, both hardware and software. So we get a kind of instability in our environment. This means that the last week, the upgrade was last weekend, and last week we were not able to run in a perfect conditions the runtime. There are also delays. We have now also new file systems that we are testing, and there are people that are waiting for that, and they will be soon completed. So for doing the video, the demo, what we did was to record a demo. Okay, so I'm going to share the video. Is this one? Let me see. Can you see the player? Can you see the video? Okay. Okay, it's 5 minutes, but I think that some parts can be speeded up. Okay. So this is in Tucan. We just run in the intelligent controller. We run the controller that just executes the applications. Slab was not integrated yet. So it's the intelligent controller that runs the applications. In this case, is Jacobi application. This is the log, the output of the running applications. Usually it's dumped into a file, but we use the screen. So basically what we do is we start running with one process. We know the existing processes that are 8 cores. So we apply, I'm going to pause here. The system knows that there are 8 cores. Given that this is the only one, you see here is running only with one. What we do is the intelligent controller sends using the RPC a command for expanding, creating 7 new processes in the application. Okay, so this log belongs to FlexMPI. Basically, it receives the command that is running a certain compute node, and it creates 7 processes. That is here. There is an internal timestamp here. So now the application that was before running with 1 compute node, just at the very beginning, now if we look at here, can you see the number? Can you see the number? Can you see clear the font?
Yes.
Yes, okay. It's 8 now, okay? These metrics are collected from the FlexMPI. So we get the flops, absolute flops, mega flops, okay? Take into account the execution time between different sample intervals changes according to the number of processes. So now the mega flops are increased a lot using 8. Then we have different metrics of communication time, I/O time, processor time, or wall clock time. Okay. We can see here that there are 8 instances. In green, we can see the threads. The threads is 1 thread that is FlexMPI and 3 extra threads that are related to the RPC library that is being used. Okay, so there are in total 4 threads per application. Okay, so we get information about iteration number, metrics, and now at a certain time, another application is going to be executed. In this case, is the gradient, conjugate gradient application. Okay, so before executing that, given that the intelligent controller is working also as a SLAM, in this example, we know that it's time for running the new application, so we need to allocate resources. So what we do is just basically, we reduce the number of processes by 4. So now the new size will be only 4. Okay. So we have allocated new space, and now we will run the other application, that is the conjugate gradient. It is originally executed with 1. Okay. But then it's expanded to 4. Okay. So now you see here we have different iterations, because on the screen we are looking at the output of both of them. Have Jacobi using 4 resources, and conjugate gradient using should be 4 also. Yes, there are 4 of them in here. Okay, with different performance. So we are sharing the node, adapting to the existing conditions, and then after a while, the conjugate gradient finish terminates the execution. It's here. There is a special signal that is sent to the intelligent controller just to notify this end. So when it's aware, it expands the original application, that is Jacobi, again to 8, because all the resources are available. So new processes are created. It's a bit later. Okay, here it terminates, and here the Jacobi, the original one, is expanded, creating new processes that we see here. Okay. So this is just an example of just coordinating different applications, monitoring them, and taking decisions about actions, in this case, to maximize the usage of the compute node. Okay, so the idea is that we will have the platform available when it will be stable, so you will be able to test it by yourself if you are interested, and also to integrate other components like malleability manager and I/O scheduler, at least using these examples, these use cases that we have provided, okay, as immediate actions. And that's all from my side. I think that we can finish here. And of course, now is question time. Hope that this talk was useful for you and enjoy it. So please.
Yes, well, I'll start. Can you hear me?
Yes.
Yes.
So my question is, how dynamic is FlexMPI exactly? By that I mean, if in the example you showed that we're working inside the Slurm job with a fixed number of nodes, and we just distribute it between applications. So if we can get Slurm to give more nodes to a running job, can FlexMPI use them directly, or does the application have to restart? Or
No, it's dynamic. Yes. What FlexMPI needs only is the names of the job and the processes that are related to it. And the number of processes can be positive for creating or negative for destroying the processes.
Yes, I mean in the set of nodes that FlexMPI can use. Because if I read the code correctly, using MPI spawn, and you pass a list of hosts. So can this list of hosts change during the running of the application, or is it fixed at the application start?
Okay, yeah. We have one constraint and the constraint is that I'm not sure if I answered your question, okay? But is that the original number of processes cannot be reduced. So if the application is run with 8, it is not possible to move to 6. But I think that this is a problem of at least the version that MPI we used. It's a problem of the MPI library. What we do in practice is that to launch the application with a minimum number of processes, maybe 1 or maybe 10, and then expand it. So if you want to run the application with 128, maybe you can start with a minimum number of 50, expand it, and of course you know that you can just increase whatever you want, but reduce the size minimum of 50, that it was the original number.
Yes, I think that's the limitation that they're talking about in the IMPI paper, that you can only work on the job that you spawned. So you can spawn jobs and then delete them, but you can't work on the job that started with at the start.
Yeah.
But no, that's not exactly what I meant. What I mean is, let's imagine that we have a way in Slurm to get more nodes for a running job. So there's a job running, and Slurm says, okay, here's 8 more nodes. Can FlexMPI then use these 8 more nodes, new, while running, to reconfigure? Or does FlexMPI have to know every available nodes at the start?
Okay, there is also a limitation that is Slurm restricts the access of one application to certain nodes. So just assuming that this can be avoided, because of course the decision, the action is taken by Slurm. So okay, these are additional nodes, and let you access to it. Let you access basically when we create processes. I think that internally is a remote shell action, so a RSH action. So if it is possible to establish a connection with these nodes, I think so, yes. We only need to have the names of the nodes, and using these names, just create using MPI, spawn new processes on them. So it shouldn't be any problems.
Assuming that Slurm can add new resources to our client, our current partition, FlexMPI can use the new resources assigned. There's a restriction in our files, in the configuration files, in the rank files, but we can have a list of the whole resources in the cluster in order to avoid that restriction. So assuming that Slurm can add new resources to our partition, our allocated partition, yes, FlexMPI will be allowed to use them.
Okay. Yeah. Okay. Thank you.
Welcome. David, there's a question in the chat. Laura said, does it work also for subgroups of communicators?
No, this was not considered in the current version, but I think that can be done because we are actually using a subgroup communicator. So I think that we can extend that to just consider this group and apply the operations when I just. Can you see the slides, right? Can you?
Yeah.
Yes.
Okay. So I think that instead of using this as a global communicator, applied it to the subgroup. So theoretically, yes, but we should study this thing with more detail.
Okay, I raised my hand so I can ask the second question now. Does it work for a Fortran application?
Sorry?
Okay, sorry?
You mean Fortran?
Yeah, if it is written in Fortran. Because I've seen that the examples are in C, so just...
Yeah, the examples are in C. MPI fully supports Fortran. And I know that it's possible to call C functions in Fortran and did it many years ago.
Okay.
So the answer is, again, I think that theoretically, yes. But what I'm not sure is that the MPI runtime, Fortran, because we are using it, if we can use the PMPI, write the functions, and work with the communicators in a simple way. So I think that it could be, but I'm worried about the effort, how difficult it is to, because the functions that we have in FlexMPI for C are C functions. We don't have Fortran implementation. So could be done, but I am not sure about what is the effort that we need to put.
Okay, thank you.
Maybe I have one question, if I may ask. Is it okay? Hello, can you hear me?
Please. Yes, we hear you. Please.
Yeah, okay. Actually, my question is basically related to the scheduling part. What I would like to really know, especially when you were talking about the multi-criteria objective, when you were saying about minimization of the cost and so on. My question is basically, have you considered in the past in your publications or in what you are designing, let's say, plan-based approach? Like, have you been trying to make a reservation for your resources in advance for the future, or it was always based on the current moment? Like, at the moment I have these nodes available, and then I will use these nodes for my application.
Okay. So in our work, first, we don't work with the SLAM because this was out of the scope of the research, and they are doing now. No, it's not easy. So what we created is we allocated a static partition using SLAM, but all the nodes that have been allocated, we developed a scheduler that is equivalent to SLAM that decides which are the compute nodes related to each application. So if I understood you well, this decision is done at runtime. Is purely dynamically. So if at a certain point we decide to migrate the application, we look at the compute nodes that are available, and we use one of them to move the application, which means moving processes from this node and moving them to the another. So it's dynamic. The answer.
Yeah. Okay. Well, my assumption is also I'm talking about dynamic approach here. But what I would like really to know, like for example, are you working like with wall time, and you say, okay, I have this application which is expected to finish after 3 hours. It means I will make a reservation for another application to start after 3 hours on these compute nodes. Have you been considering such kind of things in the past?
No. Our approach is on demand. So we run the application. We assume that you have a profile of the application without interference, which means run executive in an exclusive way. So we know the communication, I/O, and CPU time per iteration during the whole application. Can be constant, or like in Epigraph, can be changing, can be variable. So we work on demand. So if at certain time there is a degradation, then we take action. We trigger, we have a threshold, of course. If the threshold is passed, then we decide to move the application. So we don't pre-allocate. We use the resources that are existing at certain.
And you think like basically, because I'm interested in Admire needs and so on. You think in Admire we are not going to use such kind of techniques, like to make some kind of planning for the future?
Yeah, this is related to Mark's comment in our previous meeting. So my point of view that the static techniques, especially with I/O, with CPU, is difficult because in the worst case you can just run the applications in different compute nodes and over, no problem at all. But with I/O, you can get interference very easily, even if different nodes are used. So it's very difficult to model that statically. So my experience at least is dynamic techniques should be used.
Yeah, but just probably to clarify it, when you are using plan-based, this is not static approach. This is dynamic, because you can do replanning, rescheduling over again and again. Yeah, so it's not really static scheduling, but it has the advantage of like considering several jobs at once or several applications at once, and you can do optimization for several jobs at once.
Maybe we can discuss, exchange papers, and
yeah, definitely.
More questions?
Yeah, thank you.
Welcome. More questions? Barbara, Jesus.
I don't see any. I don't see any in the chat or any raised the hand. I don't know if
It's
someone
time.
wants.
It's just the end of the schedule to finish.
Thank you.
So thank you very much for your attention.
Sorry.
No, sorry, Jesus, just give thanks to you, and I am available by email if you have further questions.
So thank you very much for the presentation, David. I think has been very interesting, and for the people of the project, this is the kind of things we are doing for FlexMPI that can be implemented in the intelligent controller. When we connect this application with SLAM, we hope we can extend the functionality to SLAM directly. So thank you everybody for attending. I think we are finishing the presentation, so we will close the recording now. And remember that the video will be available in the web page, in the Admire web page, under dissemination, okay? Like all the other webinars that you can see, or if you think they're interesting for other people, even in your research group outside of the project or something like that. And thank you, Barbara, for the hosting of the conference and the preparation for all the things.
Okay, thank you all for attending, and just a reminder, if you want to propose new webinar, please do it. We have a free slot for the next 2 weeks, so
yeah, I am talking to the people of applications to have at least 2 webinars related to use cases. Okay, so as soon as they have the date, we will propose a new webinar for the applications. So thank you, everybody. I think we are closing. Barbara, you stop recording. Probably